Hey everybody, I'm Jarrell with Jarrell Education. Today we're going to be going over a pretty standard physics problem where we have a mass on an inclined plane with and without friction. Before we get started, if this video helps you and you're just starting out your mathematical and physics journey, it would really help if you like and subscribe to the channel. Alright, let's get into it. What we have here is a mass sitting on a flat surface, and I'm about to take that surface and start rotating it up. Now, as I rotate it up, I want you to pay attention to what happens to force normal, and I also want you to look at the components of the gravitational vector. Pay particular attention to how force normal is shrinking and staying the same size as the component of gravity. Also, pay attention to the angles that are equal to each other. Now pause the video and make sure that you understand this picture before we get into our problem. Okay, so what we're going to tackle now is a classic problem from a first-year physics course. We have a mass on an inclined plane. Now the mass we have is 8 kilograms and it's inclined at an angle of 30 degrees. We're also going to let g, the acceleration due to gravity, be 10 meters per second squared. Okay, so when I draw this, if you're taking something like the AP test, they're going to have you draw your free body diagram and they're going to represent the mass by some sort of dot. And they're going to tell you to draw the forces as pull forces, meaning the force starts at the dot and it moves in the direction that the force is pulling. So what we know is we have gravity, so I'm going to point that this way, okay? Now that force is going to be mg, and since g is 10, that's going to be a force of 80 newtons because the mass is 8. We also have force normal indicated here, which is the force that's perpendicular to the ramp. So we'll call that Fn, okay? Now that's it. Those are all the forces that are acting on this. Now what we tend to do is this. We know that the mass is going to accelerate down the ramp in that direction. So we impose a coordinate system where this is our y-axis and our x-axis is parallel to the plane. And we do that so that the acceleration, let me draw a little a there, the acceleration, one of the axes points in the direction of the acceleration. Okay, so now let's start filling this in. We don't have to break up force normal because it lies on an axis, but we do have to break up the mg vector. Now, I think your best bet when you're breaking this up is to do this. Listen carefully to my words on this. You're going to pretend that the vector you're breaking up is the diagonal of a rectangle that you didn't yet draw. Here's what I mean. From the tip of that vector, I'm going to draw a line back perpendicular to that axis and a line here perpendicular to that axis. In fact, let me zoom in on just this spot. Okay, now, one of the components of gravity is going to be there, and one of the components of gravity is going to be there. Now, hopefully it's clear to you that this angle right here would be the same as the ramp angle, in this case 30 degrees. So let me just say something about that quickly to make sure that you're okay with that. If you look, I'm just going to do some geometry here. If you look at this triangle right here that I'm making based on the vectors that I have, okay? That would imply that this angle, well, this angle would be a right angle, which means this angle would be 60 degrees. But also, between these two axes, that's a right angle right there. So if this one's 60 and I have a right angle, this one's going to have to be 30. Okay, so that's always going to apply. Now let me back off some of these, get rid of them. All right, there. Okay, so now, anyway, what I want you to take away from this is this angle right here is always going to be the same as the angle of the ramp, okay? Now, what I'm going to look at is this triangle right here that I'm drawing now in purple, right? That's a right triangle, okay? So this component right here, since the vector itself is like the hypotenuse of that triangle, this is going to be, I'll go off to the side. We could say, if I call this, let's say I call that y, we can say that the cosine of 30 would be equal to y over the hypotenuse, which I know is 80, the length of the actual gravity vector. And when I cross multiply, I'm going to get y is equal to 80 times the cosine of 30. Now, 80 times the cosine of 30, when I calculate that, is equal to 69.28. Okay, so I know that this component here, let me just make a little bit of room here. Okay, I know that this component vector is going to be 69.28. Now, by the same argument, I'm going to figure out what the length of this line right here is, but that's actually the same as that component, right? So that's going to turn out to be, for the same reasons that I just showed you on the one leg, that's going to turn out to be 80 times the sine of 30, because that's the opposite side. And 80 sine 30 is simply equal to 40. Okay? All right, now that we broke the vector up, let's have a look at this. Let me zoom back out a little bit. Okay, so I think you're probably okay with the fact that force normal and 69.28 have to be the same, since there's no acceleration happening in that direction. And that's fine. You could just right now say Fn is equal to 69.28. But for a little while at least, I'd prefer that you wrote the summation of all the forces in the y direction is equal to ma. And then we note that the acceleration, may, the acceleration in the y direction is just 0. So I can say that Fn, because it's up, minus 69.28, because it's down, is equal to 0. And that means Fn is equal to 69.28. Okay, so now I figured out what force normal is. Now let's take the x direction. The summation of all the forces in the x direction is equal to m mass times acceleration in the x direction. But if you notice, there's only one force in that direction. That's how I know it's going to accelerate that way. Let me scroll up a little bit. So I have 40 is equal to the mass, which is 8, times ax. So that means ax, when I divide both sides by 8, would have to be 5. And the unit would be meters per second squared. So there you go. We figured out the acceleration down the ramp with no friction. Now, let's get on to a problem where there is friction. Okay, now we have the exact same problem pretty much, with the exception of friction, okay? So the mass is still 8 kilograms, it's still tilted at an angle of 30 degrees, but now the coefficient of kinetic friction is 0.4. Now remember what I said in my last video, and if you haven't watched it, go back and check that out before you try this, okay? Frictional force, there's a formula for it, it's just, frictional force is equal to mu sub k in this case times force normal. But rather than having that be another formula you memorize, I suggest you memorize it as the frictional force is always a percentage of force normal, and mu sub k is that percentage. So that just makes it easier, at least in my mind, to not have to memorize another formula and calculate friction. So I've already drawn the free body diagram like we had. The only thing I added in was I added in friction. So now we have to calculate that. Now from the last problem, we already know that Fn was equal to 69.3. Okay, so from what I just said, that would mean, let me scroll up a little bit, that would mean that the frictional force is going to be 40% of 69.3, which turns out to be 27.7 when you calculate that. So now I know that the upward frictional force is 27.7 newtons. And now we want to figure out what the acceleration is down the ramp. Now remember, when there was no friction, the acceleration turned out to be 5. Let's see what we got now. The summation of all the forces in the x direction is equal to ma. Okay, I think you should always start by writing that out. Now, in the x direction, I've got 40, which is the winning force in that direction. That's actually pulling it down. And then friction is opposing it in that direction. So the forces are still out of balance. So there's going to be an acceleration. So here's how we would say it. 40 minus 27.7 is equal to 8a. Now 40 minus 27.7 is going to be 12.3, and that's going to be equal to 8a. And if I divide both sides of the equation by 8, write that over here now, a turns out to be 1.54. And again, the unit on that would be meters per second squared. So that would be the acceleration now if I include this 40% friction, 40% of force normal friction, okay? So it's significantly less than it was when there was no friction, all right? Done.